Hey everybody, so this video is to show you the proof of the quotient rule, which I've written up here on the screen. When you're taking the derivative of a quotient of two functions, it's bottom times the derivative of the top minus top times the derivative of the bottom divided by the bottom squared, or low d high minus high d low over low low. So when we do this proof, we're going to start by using the h definition of the derivative and plugging x plus h into f of x over g of x, and then subtracting f of x over g of x, which is what you get when you plug in x, and dividing that all by h, and doing the limit as h approaches 0. Now, we've done that before. So what we get here is something that gives us 0 over 0 if we were to plug in 0 for the h. Now, when we had fractions in these indeterminate limits before, we got sort of worked with it by combining the fractions into 1. So I'm going to do that here. So I'm going to get a common denominator between these two fractions, and that would be g of x plus h times g of x. I'm going to combine those two fractions into 1 by getting that common denominator. So I'd have to multiply this by g of x, as I've done here, and I'd have to multiply this by g of x plus h, as I've done here. That would give me a fraction, a single fraction, divided by h, which is the same as multiplying that fraction by 1 over h. So this would give me a non-stacked fraction at this point. Now, if I were to plug in h again, I would get 0 over 0, so I'm not even going to bother to do that. What I will do, though, is revert to that thing that I did in class today with the product rule of adding a special form of 0. But this time, the special form of 0 is going to look a little different. If you notice we had an f of x plus h here, we would like a minus f of x, so we can actually get something that looks like the top of the derivative. And then for this thing, we have a g of x plus h, so we're missing the g of x part of that derivative. So when I add my special form of 0, it needs to have an f of x for this part to complete this, and a g of x to complete this. So my special form of 0 this time is going to be f of x times g of x added and subtracted. And you see I've done that here. So now it's all that algebraic manipulation. I'm going to start by grouping the first two terms, these two, and pulling out their common factor, which would be g of x. And then I'll group these two terms and pull out their common factor. But if you keep in mind that the derivative definition has g of x plus h being positive and g of x being negative, in order to make that work, we would have to reach in here and pull out not only an f of x, but a negative f of x. So when I factor this out, it's going to be a negative f of x pulled out, and that changes the signs on both of these things so it looks like what's in the definition of the derivative. So now that I've got that factored out, I'm going to break this apart. And the way I'm going to break it apart is I want to take all the stuff that's relevant to the definition of the derivative and sort of group it together in one fraction, and then shove everything else off to the side. So this first part of the fraction, everything that's relevant to the definition of the derivative is this f of x plus h minus f of x over h. That goes here. And then everything else that's in that fraction is g of x over g of x plus h times g of x. So I shoved that here. By the way, I know I could simplify that. There's a reason I'm not, and you'll see that in just a couple of minutes. And then over this side, the thing that's relevant are the g of x plus h minus g of x over h. That's here. And the rest of what's here is f of x, the g of x plus h, and the g of x. And that's here. So now what I'm going to do is actually take the limits. As h goes to 0 in this fraction, the g of x plus h becomes g of x. So what I get is this. Now I know, again, I could simplify it, but I don't want to, so let it be. So as h goes to 0, f of x plus h minus f of x all over h is f prime. Here, the g of x plus h would again go to g of x, and that would look like this. And then the limit as x approaches 0 of this stuff is the definition of g prime. So now it's just a matter of combining things. So I have a fraction times something that's not a fraction, so something over 1. So that would basically multiply to the numerator and look like this. And same thing here. And now I want to combine these fractions. Now this is why I didn't simplify before, because these two fractions now I want to subtract, they already have a common denominator. If I had simplified it, I would have had to gone back and unsimplified it to get the common denominator back. So now that I've got the common denominator, I can simply combine the numerators by subtraction, keep the same denominator, and there's the quotient rule. Hopefully this helps you understand where the quotient rule comes from. See you soon.